Hello and welcome to day 2 of our event. I will just explain a little bit about what you can find, what you will see today. Thank you for joining us again today. To this event, best available techniques and practices for mercury emission reductions from coal-fired power plants in Indonesia. Sorry, my screen seemed to have frozen. I would like to explain to you just a few things about how to ask questions. If there's any questions after the presentations, you have a little question pane at the bottom of your control panel of GoToWebinar, and you just type in the questions there and hit send, and speaker will be able to see your questions. Wait, now it works. Here we are. So welcome to day 2 of our event. Here we go. So I'm just going to run through, if you can see the screenshot I've made here. Here is where the panel where you put in your questions, and everyone will be able to see them on our side, and we'll do our best to answer them afterwards. Again, I'll say again, tomorrow you will have to sign in with the same link. So yeah, everything is same procedure as yesterday. And I think that's all from me now. I'm now happy to hand over to Wojciech Jozewicz of the AEA. Over to you, Wojciech.
Thank you, Benedict, and thank you for this introduction. Hello, everybody, and good very early morning from North Carolina on the east coast of the US, some 11 hours behind sunny Jakarta. I am Wojciech Jozewicz with Atlantic Energy Associates based in Raleigh, North Carolina. The subject of my presentation today is presenting to you how to use the iPOG to obtain emission estimates. And estimates is the key. iPOG only provides estimate. It needs refinements to provide exact data of the kind that would be used to build national inventories. iPOG, of course, stands for Interactive Process Optimization Guideline. Now, my screen froze and I cannot forward my slides. Let's see. It froze. Les, could I ask you to take control of the slideshow? And we'll be asking you to flip slides for me. I'm sorry, but my screen froze.
Is this working?
Thank you. Yeah, I can see your screen. Thank you. Could I have the next one, please? Yes, I have it. Thank you. Sorry for a glitch, folks. Don't know. Computers have mind of their own. So let me begin with the outline, and I will start my presentation by summarizing the groundbreaking study that's been performed by Basel Convention Regional Center under direction of Pak Anton and Pak Erlanga. Then I will lean on that cornerstone to present how it evolved into our current Department of State funded study, present the objectives. As you have heard yesterday from Les, there are several phases to the project, and we have just completed phase 1, which this workshop is the culmination of, but there will be following phases. Importantly, we intend to heavily lean on stakeholders, because experience shows without active participation from stakeholders, you don't have much of a project. The core of my presentation will be spent on discussing analysis with iPOG and how this analysis contributed to laying the groundwork for selection of phase 2 plans for further studies. Can I have the next one, please? So let's begin with the study from 2016, actually, and it was published late in 2017. It was the so-called small-scale funding agreement by United Nations in cooperation with Basel Convention Regional Center and Ministry of Environment and Forestry. During the duration of the study, UN decided to change their name from United Nations Environmental Program, which is what UNEP stands for, to UN Environment. So pardon me if I use these two terms interchangeably. So while the technical lead was done by BCRC, team included specialists, obviously from Ministry of Environment and Forestry, but also specialists from Ministry of Energy and Mineral Resources. So we had very good technical team and buy-in and approval from the government of Indonesia. The work was funded by UN, but was performed under auspices of UN Global Mercury Partnership, co-combustion area, which Dr. Sloss is the president. So at that point in time, 2017 study was the most recent comprehensive study of coal-fired power sector in Indonesia, and I will explain more in the next slide, please. The scope of the study was as follows. It concentrated on presenting current relevant information for improvement of future emission inventories. Of course, as I said, it started in 2016, which was the time that Indonesia was getting ready to ratify Minamata Convention, which happened in 2017. So the report provided in-depth overview of coal sector, coal production sector, coal markets in Indonesia, and then characterized power sector. This included all forms of energy generation, but obviously with the focus on coal-fired. Some highlights from the study: BCRC provided analysis of coal samples for 47 units and conducted measurements of mercury emissions at 3 power stations, and this included providing speciation of mercury. Speciation, of course, is the term that describes how mercury evolves, and 3 basic species of mercury is elemental mercury, oxidized mercury, and so-called particulate matter mercury. So mercury bound to particulate matter, either physically or chemically or both. Then they focused on concentration of mercury in bottom and fly ash, which is important from the aspect of mercury control at power station, and provided first estimate of emission inventory for coal-fired energy sector in Indonesia. Do we have the next one? So the study finished with recommendations to improve mercury balances at power station sampled in 2017. There were some issues with closure of balances, which was not a surprise. Mercury, as you all know, is quite elusive element, and it's often difficult to balance. Then a study recommended the consideration of application of method 30B for monitoring requirements. I believe Roger will spend some time on it tomorrow, discussing in more detail. So it will suffice to say here that it's a US EPA method that provides for monitoring of mercury emissions, and at much lower cost than conventional CEMs, or continuing emission monitoring. Further on, the study suggested detailed analysis of the sector. Of course, cost is important, so study recommended cost-efficient solutions that would comply with future national implementation plan. And again, they recommended extensive stakeholder activities. Next, please. So the way we see stakeholder activities, they are all-encompassing and are designed for different groups. There will be different discussions with general public and about concerns that they might have resulting from operation of power plants. There'll be different discussions with technical workers at the power plant, and then with government officials who are, of course, interested in overall picture and implementation of policy. So we need to generate awareness of stakeholders, NGOs, media workers, and so on. In the process, we'll need to describe methodology behind CEM usage and policy, and also methodology to monitor mercury emission, how it's going to be implemented, how public will be informed, and how the law will be carried out by government to enforce activities. Ideally, CEM information should be integrated across the sector and beyond, so that it's easier for government officials to keep the hand on the pulse, so to speak. Future data, of course, should be well defined, and informational exchanges should be going on. I couldn't say enough about the importance of stakeholders' involvement in the process. Next, please. So now let's go to this project funded by U.S. Department of State, for which we are very grateful. Again, this is describing phase one. So the first objective was to utilize the UNEP tools, mainly iPOG, to update 2017 estimates of mercury emissions from power units in Indonesia. Of course, at 2017 it was very current and groundbreaking, but here we are in 2021. Time flies, so we need to update and make estimates more precise. And then major objective was to select 3 coal-fired electricity generating units for more detailed study in phase 2. In the process, our objective is to work very closely with the ministry and BCRC to prepare these 3 cases for improvement to stakeholders during phases that will follow. Another objective for phase 1, which we have done, and you can see it in the report, is to define data needs, initiate exchanges, which we had frequent exchanges with BCRC and attended by ministry officials occasionally, and to use iPOG to model units of interest for future mercury reduction strategies. Next, please. Could I have next slide, Les? Thank you. So Paul has covered it in detail yesterday. So just briefly, I'll mention that BCRC, the report that is available online, was our baseline. We have improved the data with the set of September 2020 data from BCRC, and then augmented it with input from SAP. But data is what it is, and data will need to be refined in the following in the phases that will follow, following the guidance from BCRC and the ministry. Next, please, Les. So the rationale for the project is utilization of UN tools such as iPOG whenever possible. You will see various in this rationale of Department of State funded project. There's a lot of overlap with agenda of UN. Department of State has excellent record of being very supportive of UN objectives, and I had a privilege of being involved in a few projects that were funded by Department of State, but focused on supporting UN goals. Of course, we want to comply with that BEP approach that's been outlined by UN. But BEP is best available technique, best environmental practice approach, and this is a set of documents for different industrial sectors, including coal-fired power generation and industrial boilers. It is important, as discussed before, to obtain approval from the ministry and BCRC as far as sites and technologies that selected, so that we are in full compliance with countrywide NIP for Minamata Convention implementation in Indonesia. Next slide, please. So now let me spend a little bit of time describing database processing and selection criteria for phase 2. We have, of course, started with a huge number of units in our database. So we have divided this data set into 3 subsets. Large units without flue gas desulfurization, which was majority of units in the database. Then we had second subset, which was large units with FGD, whether seawater FGD or with limestone FGD, combined together FGD. And the third one was for units that were smaller than 100 megawatts. So obviously, I mentioned larger units were units larger than 100 megawatts. And we have focused on these units that were bigger than 100 megawatts, simply because this scale is typical for power generation. Units smaller than 100 megawatts are not typical and are not critical for national grid, but may be heavily polluting locally because there's a large number of them, and not often they are not controlled very well. Then I should go to the next slide. Thank you. Which is how to present presentation of UNEP tools. So both tools are on the Coal Partnership website, and the first one is a about 100-page process optimization guidance document that's been published in 2010, early in the days of Minamata Convention negotiations, when UN realized then set of information is needed to be shared by negotiating parties, and then they commissioned this report. Following the paper study, we took the approach from POG and converted into iPOG, which is interactive POG. I like to think about it as a deceptively simple model. It's been built by Dr. Stephen Nixa, and Steve was one of key participants in Mercury program in the US. So he is a top expert in knows Mercury control in and out, and his team built this iPOG that I will describe in more detail later. Here you can see on the slide that it uses, it's very visual, has good interface, uses simple self-explanatory icons, of course, coal pile, furnace, SCR, heat exchanger, ESP, wet FGD, and stack, and flue gas coming out of stack. Next slide, please. So let me now tell you how we use the iPOG and POG, what it does. Both tools were designed to promote options that improve overall minimization of emissions from plants. So while focuses on Mercury, it addresses minimization of emissions of number of pollutants simultaneously, and emphasizes co-benefit approaches for mercury removal. Co-benefit is the term specific to mercury emissions control that describes the property of mercury in flue gas, that it can be controlled by devices that have been not necessarily designed for mercury control. For example, flue gas desulfurization, obviously, as the name suggests, has been designed for control of SO2. However, it happens that it can be very effective in controlling mercury as well. So co-benefit is the term, key term here that we try to utilize as much as we can. Once we had POG and iPOG, it's been used by UN to develop BAT-BEP documentation. You can see it when you go to BAT-BEP, which also is available on UN website, that how it follows the steps of POG, which POG and iPOG are sister and brother. Next, please. So how does it work? If you imagine power plant and flue gas control equipment, these are the different layers that describe control of pollutants. So the first step is to control oxides of nitrogen. So then we ask ourselves the question: is there an NOx control like SCR, or is there not? Well, if there's no control, we go to the next step, which is ESP, which is particulate matter control. And then we ask, do you have fabric filter? Do you have ESP? If you have ESP, you go to the next step and see, okay, let's see if I have SO2 control, which is the next layer and final for control of pollutants. And if you don't have SO2 control, either wet or dry, the POG directs you to this little ellipses at the bottom, which are options for mercury control. So, for example, if you don't have NOx, you have ESP, you don't have wet FGD, your options are ESP tuning, maybe some injection of activated carbon, which I will discuss later, or treatment of coal. Next, please. So let me show you an example of how screens look in iPOG. So this is the initial screen when user decides about configuration of air pollution control. This tab here opens possibilities. So I've selected here ESP only, and you can see there is ESP and nothing else between ESP and the stack. No post-combustion, no SO2. Next, please. Once we have configured our system mirror what we want to consider, the next screen opens up for call. And call can be call input is quite flexible in iPOG. It can include one call, single call properties here, that tab, or it can include blend of up to 3 types of call, which call blending, by the way, is one of strategies to maybe one of the strategies to control emissions. The input includes higher heating value. In this case, yeah, we're using sub-bituminous call, which is somewhat typical for Indonesia, with what we would describe in the US as low sulfur coal. However, in Indonesia is pretty high. Reasonable chlorine, fairly high mercury concentration, 100 ppbs. The iPOG uses higher heating value of coal. It's important to point out that users should input the sulfur and chlorine content of coal, because these two elements have very significant effect and can affect how mercury behaves in the system. Obviously, mercury content needs to be inputted, because the more mercury you put in, the more potential we have to push it through the stack. Next, please. So after we have done all this inputs, and there are other screens that define furnace, which I skipped for the sake of brevity here. But so we finally come to the results, and this is a snapshot of mercury behavior in the system based on input parameters, iPOG estimates, mercury emissions. It is capable of predicting the amount of oxidized mercury and elemental mercury. Remember the mercury speciation, and then gives the user mercury removal, as expected in this case, with only the ESP fairly poor, less than 4%. It's also worth pointing out that iPOG gives an estimate of outflows of mercury from the system, which is mercury content in the fly ash collected by the ESP, and however small amounts of mercury collected in the bottom ash. Could I have next, please? So iPOG is a very good tool, but it's certainly not a panacea. So we need to keep in mind what iPOG can and what cannot be used for or shouldn't be used for. iPOG is very good at qualitative ranking of emissions for units where there is enough data, because otherwise one needs to improvise and assume, which is not very good. It's better always to have good data. It is good for selection of methodology for reduction of mercury emissions. It's easy enough to flip those icons on screen, and then again, what looks very simple is quite extensive set of equations developed by Steve to calculate the behavior of mercury. Importantly, it's excellent platform for discussions with stakeholders. We have experienced this in a number of countries, and iPOG has been fine-tuned as a result of its very valuable discussions. However, of course, iPOG has its limitations. It shouldn't be used to build an emission inventory, national emission inventory for mercury SO2. Obviously, more precise information is needed for that. It shouldn't be used as policy tool for NIP. iPOG is for illustration purposes, if you will, but more precise calculations needs to be done before implementation. Next, please. So in summary, we have shown how to estimate mercury emissions from coal-fired units using iPOG. And we have, again, based it largely on a groundbreaking study from 2017. We have analyzed the emissions from individual units, and Dr. Sloss will have a presentation later on that will describe in detail. So we have again analyzed, we have divided our database into 3 units, 3 sets. Large units without FGD, large units with FGD, and smaller, less than 100 megawatt units. And of course, iPOG tool is available as a free download from UNEP website, the link that you have been shown yesterday by Les. I think that's it. Go to the next one. Yes, thank you for your attention, and I will try to answer any questions that you may have. Thank you.
Thank you, Wojciech. We actually have 2 questions that have come in. The first question is, what is the most common compound that mercury forms during combustion? Is it as a solid or as a vapor?
Yes, thank you. Mercury that is contained in coal is of course vaporized in the furnace. So initially all mercury is in the vapor state, and then as thermal equilibrium changes, mercury and temperature drops, mercury starts oxidizing. And then as temperature drops even further, then some of the mercury is bound to fly ash particles or unburned carbon particles, preferably, either physically or chemically or both. So to answer the question, there is initially all mercury is in vapor phase, but then as flue gas undergoes transformation, the speciation happens between gaseous and particulate mercury.
Thank you. Another question, can the iPOG be tuned depending on whether there is plant-specific data, or does it only use its own default values?
Oh, very good question. Very good question. Thank you. And yes, 3 times yes. iPOG can be fine-tuned and should be fine-tuned. That's the beauty of it, that it can use exact data from the power plant, and that's what we're hoping to achieve in phase 2 after interactions with stakeholders, that we will have confirmed data that we have and use actual data. Of course, one can run iPOG on default values, but that's just just an illustration of training maybe. But the beauty is that yes, it can be fine-tuned for actual data.
Thank you. One final question from Indonesia. How many power plants are there in Indonesia? I suppose power plants versus units. Can you remember off the top of your head?
I remember that we started with about 300 units.
Yeah.
And then we narrowed it down because of incomplete data. I believe we've narrowed our database to about 100 units.
I believe so. I think there's about 111 or something. Paul can maybe step in and help us there. But that's units. Often power plants have more than 1 unit. So I believe there are about 40, 45 power plants in Indonesia. Does that sound about right?
That sounds about right. And I would refer the question, the person who asked the question to BCRC report from 2017 that gives this information about, among other.
Yeah, thank you. Okay, well, that's all the questions we have for Wojciech. I am now going to, if that's all right, take over and come up with some of the results. Hopefully you can see my screen now. So thank you, Wojciech. Over the last day and a half to where we are now, we've gone through how we got the data to crunch through the results. And so I'll just remind you of that. We collected over 40 fields of data for each coal-fired power unit. And as I've said, there are over 100 of those that are over 100 megawatts that we've included in the study. We ran the estimates and all the data we could get through the iPOG estimation tool that Wojciech has just shown us. Excuse me. And then we managed to estimate emissions on an annual basis over the remaining plant lifetime. Now, we have to put a lot of caveats and emphasize that we've made quite a lot of assumptions in doing this. We've assumed, obviously, that all the data we have are correct. We must assume that all plants run consistently over the year and will continue to do so in the future. And we have assumed that all plants will run until they're 40 years old. Now, obviously, these are significant assumptions. They are business as usual assumptions, and they're almost worst case scenario assumptions, as we've assumed that none of these plants will increase their efficiency or do any upgrading or put any control technologies in place. So this is more of a guesstimate than an estimate, if you'll forgive the term. But we needed something to start from to look at the emissions coming out of these plants. So, as I say, the estimates for each plant have been made on an annual basis, how much they're emitting every year, and also on this predicted lifetime emission over the remaining lifetime, assuming they close when they're 40 years old. So, finally, some results. Now, as I've said, there's over 100 units, so to put them all in one graph would be, you wouldn't be able to read any of the plant names and it would be rather disappointing. So what we've done is just focus on the top 30 emitting units here based on annual emissions. So this is what these plants are emitting annually right now, assuming they're running consistently. It's only a snapshot of information, and it would be very much a mistake to make any policy changes based on this information, as some of these plants may be old and due to close, others may run for years. Some may change the way they function, some may be high capacity backup sources these days, but that may change in the future. So we need to identify plants where we can reduce mercury emissions effectively as part of the existing plant group. So should we be looking at any specific category of plant? For example, the general public will always assume that the bigger the plant, the greater the emissions. And this is not exactly the case. There are lots of different factors that are going to affect the amount of mercury coming out of the plant. Initially, obviously, the amount of mercury in the coal, but also the amount of coal that's burned in the year, and any control technologies that are in place, and the utilization rate of the plant. So what we see here is a scatter graph of the mercury emissions, annual mercury emissions in kilograms for each of these units not identified, just broken up by size, so that we can see obviously the smaller plants are tending to emit less, because they're smaller plants. They can't fire as much coal as the larger units. But we have some larger units that are emitting a large amount of mercury because they're used constantly, or at least a high rate, but we also have large plants that are running quite a low rate and so are emitting less than, say, medium-sized units. The whole point of this graph is to show you that there's no point targeting units over a certain size necessarily. That would be a rather gunshot approach to the whole process. Plant size is not the most important factor. The most important factors relate to the amount of coal burned, how often the plant operates, whether it's a baseload plant or a peaking plant, and how cleanly the plant runs. More efficient plants obviously are going to produce more power for less coal burn. Also, some plants have emission control technologies in place that can reduce emissions effectively. So perhaps the more pertinent question is, do all plants emit mercury at the same rate? And absolutely they do not. They're within the same zone, but there are quite differences in terms of how much emissions. So here we're looking at, on the left and the up graph there, is the predicted mercury emissions intensity in grams of mercury per gigawatt hour of energy produced. So it's not the amount of coal burn, because some coals have more ash in them than others, some burn more cleanly than others, and some plants are more efficient than others. So what this is showing is really a sort of value factor, how much mercury is coming out for each megawatt or gigawatt hour of power that is coming out of these units. Basically, it's a simplification of how cleanly these plants are running. And again, it shows, because we've split up by unit size along the bottom here, it shows that plant size doesn't really affect the emissions that much. We have some clean burning big plants and some clean burning small plants. The majority of the plants are emitting mercury in between 5 and 75 grams of mercury per gigawatt hour, with an average there in that orange line along of around 25 grams of mercury per gigawatt hour. Now, to put that into perspective, that is almost identical to the intensity of plants in the USA prior to the introduction of the MATS, the Mercury and Air Toxics rule. So it's just to show you the Indonesian fleet is running no cleaner or no dirtier than the plants in America were before they started to install mercury control strategies. Now, I know your eyes are being drawn to these two outliers on the far left, the top left there. Those are small plants where the reported value is extremely high. These have significantly lower gross electricity productions. Basically, these plants are older and they're inefficient units. And we'll actually be talking more about one of these later. So don't worry about those. Those are not representative of the fleet in Indonesia. As we can see from this, the fleet in Indonesia is as clean burning as the US fleet was before it started to put in control technologies. So the important point at this stage is to notice that some units are emitting significantly more mercury than others just because of the way they run and the coal that they burn. So let's look at the results of the ranking. Now, as I say, this is the remaining lifetime emissions of mercury in kilograms. So this is assuming that each of these plants, the top 23 plants, because each of those is emitting over 1 kilogram, 1 ton of mercury over their whole remaining lifetime. So if some of these plants are maybe 5–10 years old and have 30 years left to run. Some of them are younger than that, some of them are older than that. So this takes in what they will emit if they continue to run at exactly the same rate they are now until they close at the age of 40. Obviously, there are missing plants off the right because there are over 100 units. We've not included those because we wanted to focus on the top 23. However, the existing fleet, the total existing fleet could emit more than 70 tons of mercury over the remaining lifetime, worst case scenario. Units under 100 megawatt, which we kind of excluded from the study, will contribute around 18% of this total. So there's an indication that 18% of emissions or so could be dealt with in the smaller units, maybe upgrading those or closing them down and replacing them with larger, more efficient units. But we're focusing on the larger plants, as the larger plants are where cost-effective control technologies such as sorbents and FGD are going to work best. So as I said, there are valid reasons. We're not naming and shaming. There are valid reasons why these plants are emitting more mercury than others. They may be younger. They may be in high demand. They may be baseload plants, and they may be very necessary to the grid. For example, Cirebon 1 there is predicted to have the highest emissions of almost 5 tons of mercury over its remaining lifetime. It's a 660 megawatt unit consuming almost 2.5 megatons of coal a year. It is only 8 years old, and it's one of the highest fuel consumption rates in Indonesia. So this is a plant that is running full on, young plant, so therefore it's not a surprise that its emissions of mercury could be high if it continues to run in this way over its remaining 32 years of life. These other plants may be younger and may be older. These values would change if Cirebon closes early, if it slows down, if it installs a control technology. Now, the top 10 emitting plants in this slide are predicted together to emit around 30 tons of mercury over the remaining lifetime in a business as usual approach. This is around 40% of the total from the fleet. I'm going to say that again. There are around 10 units, 10 to 13 units that are emitting almost half of the total emissions from the existing fleet over the remaining lifetime. And that is super important, and that's very exciting information because it shows that if we focus on these high emitters with long lifetimes remaining, then we can spend our money wisely rather than perhaps prescribing FGD or sorbent or action across all 110 units and wasting our money on units that are actually running quite cleanly or will close quite soon. If we focus on a small number of high emitters, we will be able to control mercury very cost effectively, and we're hoping that this will help inform Indonesia's strategy as it moves forward with its decision on where to place BAT and BEP technologies. So let's quickly look back at these are the same power plants as in the previous slide, in the same order. So here they're being ranked downwards, highest emitters over the remaining lifetime. Here we're looking at the mercury emission intensity, that value of grams per gigawatt hour of mercury. So as I've said before, Chiribon, if we go back, sorry, I'm going to flip back and forth a bit here. Chiribon is the highest emitter because it's a young plant. Whereas if we look at it, it's actually quite clean burning compared to the other highest emitters. It's only emitting a high amount because it's a younger plant. If we look at Banten Suralaya 1, it's emitting twice as much mercury per gigawatt hour, according to our estimates. And therefore, as an expert on this, or a semi-expert on this, obviously spending money in Banten Suralaya is going to be more effective in terms of gigagrams of mercury per gigawatt hour. But then again, Chiribon's going to run longer. These are the things you have to consider when you're coming up with a BAP-BIP reduction strategy for your plants. Information is key, and because this information is now in this data set, the Indonesian stakeholders can play with this. They can look at how they could perhaps change the dispatch order of these plants, how they could reduce the age, how they could target those plants where they're going to achieve most effective, cost-effective emission reduction. So this is the same information as before for our top 30 or so ranking plants over the remaining lifetime, with Chiribon at the top there. And what we've done for this slide is we've put in little yellow dots which show the sulfur emissions that we think will be coming out of these plants. And this is important information when we're talking about determining the best available technology or practice control emissions. Wojciech mentioned with the iPOG, if you have a sulfur control system in place, such as an FGD, you will get free co-benefit reduction of mercury somewhere between 30 to 70, possibly even more. And so when looking at these plants, we can see plants such as Suralaya, the Suralaya units. These are burning a high sulfur coals and also releasing relatively high levels of mercury. And so a co-benefit multi-pollutant strategy would be ideal for these plants, where again we have Chiribon trying to be different, and it seems to be burning a low sulfur coal, or the coal is being the sulfur is being captured. And so looking at that plant, you may decide to go for a more mercury specific control strategy, as the sulfur emissions are not quite as elevated as they are in the other units. I'm not proposing any emission reduction strategy at this stage. These are musings, but it just shows you that information is power. When we're looking at these plants, many of these plants will absolutely benefit from a multi-pollutant control strategy, which focuses on both sulfur and mercury at the same time. And as we know, Indonesia has introduced sulfur and nitrate emission limits. And as they move forward with that, they will see mercury reduction happening at the same time in many of their plants. Moving on to the last set of data for our existing fleet, we looked at the units with flue gas desulfurization. That is the technology to control sulfur emissions. Some of them are seawater, meaning that they use the water from the local estuary, the local sea, the bay, and some are wet limestone flue gas desulfurization, which used more closed loops of water for scrubbing out the sulfur. What is interesting here is that the Python 3 Unit 2 is predicted to emit over its remaining lifetime over 3 tons of mercury. So if we go back to our previous plants, it would be ranking up with our top emitters, even though it has an FGD in place. Now, this is raising eyebrows, I'm sure. This could be a glitch in the iPOG. It could be that we're predicting that mercury coming out of the plants where it is not. However, we know from the iPOG results and from our coal analysis that these coals some of them are high in sulfur, hence they have an FGD in place, but they're also low in chlorine. And so it could be the case that a lot of the mercury in these plants is elemental and is not being captured in the FGD. That's one possibility. If that is the case, then there's a super easy solution to that. A little bit of oxidant added into that could enhance the mercury capture in these units. However, again, this is the musings of an expert based on data rather than actual plant information. What we need to do at this stage is to go to these plants and find out if the iPOG is correct in its estimates. It may be wrong. the mercury may be being captured quite efficiently. However, if it is not, then these plants would be an ideal place to test sorbent or oxidant addition. Bearing that in mind, however, we have to remember that these seawater units, anything that doesn't go out of the stack or end up in the gypsum or any other solid waste sludge material, of which there is less than out of a wet limestone FGD system, some of this material will obviously be flushed out into the local water, and we do not want mercury to be ending up in the local water. So if we do have any strategy for these plants, we will absolutely be taking the concern for the local estuary into account when we do so. So factors affecting the emission ranking, as I said, it's not a name and shame. The ranking shows up very clearly plants with more years left to run. The younger plants are going to look worse because they have more time to emit mercury. The utilisation rate, those plants that are burning a lot of coal right now look bad, but we have to remember those are our baseload plants. Those are the plants that are keeping the lights on at this point. The efficiency of the plant, our grams per gigawatt hour, is extremely useful for identifying those plants that are burning more cleanly than others. And we will try to focus on some plants that are running less cleanly. And also the mercury content of the coal is going to affect the mercury emissions over the remaining plant lifetime. So the conclusions from this stage is plant size is almost irrelevant. We're not going to be focusing on plants over 600 gigawatts or whatever. We're going to be looking more specifically at the plants of concern. And our mercury intensity value is extremely useful because it does identify plants with high utilization range, long remaining lifetimes, which are going to emit more because they're burning less cleanly than others. And also plants which are emitting both high levels of sulfur and mercury will be prime candidates for co-benefit multi-pollutant emission reduction strategies. Excuse me. And we may find that some of these plants, FGD, could be enough to reduce emissions, but only if the mercury is in the correct oxidized state. So, what my conclusions, certainly from this stage of the study, are actions that a small number of plants could actually achieve mercury reduction far more swiftly and far more cost effectively than a blanket strategy for, say, sorbent across the whole Indonesian core fleet. Information is key, information is power, and we're hoping that this information will mean that Indonesia can spend less money to achieve significantly more reduction in a cost-effective manner. So I'm going to stop there, I believe, and I'm going to have a quick check to see if there are any questions, excuse me, and have a quick sip of water before I move on. It says here, do we not have chloride data? We have chlorine data. We have the amount of chlorine in the coal for some of these plants. And Wojciech has actually used that so that we know some of these coals are indeed low in low in chlorine, and that is why we're getting higher mercury emissions, because a lot of it is going to be elemental and it's going to leave. Do these data come from the iPOG or real measurement? Combination of both, and a very good question. Thank you for that. Combination is that the coal chemistry, as we talked through yesterday, we have the coal chemistry data, so we know how much chlorine and ash, sulfur and mercury are in these coals. We know the plant specific data. We know the plant boiler size, whether they have NOx and SOx burners in place. We have everything in there. We have put actual data into the iPOG, so it is a combination of real data and estimates. And as I keep saying, it is modelling that we're doing at this stage. What it does show is that there are some plants that we know are going to be emitting more than others because we know they're younger, we know they're firing more coal, and we know that they don't have control technologies in place. This is not bulletproof, this study. However, it is showing up a lot of guidance with respect to how we will choose which plants to work on. Excuse me, I'm quickly looking for more questions. I think there's a question about costs of control technologies. I'm not going to answer that today because I know that, excuse me, Roger Brandwood is going to be talking about control technologies and monitoring technologies tomorrow. So we will leave that to him to deal with. So please do tune in tomorrow. Okay, so what I will do now is come out of this slide and I will move into my next slide set, which is probably what a lot of you are waiting for, is which plants we're going to be looking at. I will start this and then I will hand over to Wojciech. And as we know, his slides aren't working, so we'll do the forward presentation bit, Wojciech, if that is okay with you. Okay, so as I said, we got our ranking of our plants. So now we are going to choose which 3 plants we want to focus on for phase 2 of this project. We are not selecting the worst plants. As I keep saying, these are not worst plants. These are plants that are important to the grid and obviously being used highly because they are important. What we're going to do is choose plants from the highest ranking group, but we're going to choose plants that are quite distinct in their format, in their category, in their type of plant, because we want to choose plants that are different. If we choose 3 plants from Suralaya, for example, then the control technologies and strategies will be identical because these plants are identical, and that doesn't achieve much. By choosing 3 separate and distinct units, we will come up with 3 different control strategies that will be able to be replicated across a greater proportion of the Indonesian fleet. So that's what we want to do, is to come up with strategies that will cover most of the fleet and allow some form of replication. Now I'm about to name 3 plants. We are waiting for full confirmation that these are the plants we will be working with. If we're not working with these units, we will choose units that are very similar to these units. So I'm hoping I'm giving you the information that will be relevant to any decision or any proposal that any of you control technology purveyors out there might want to come back on. Okay, so we've chosen an older unit which does not have FGD in place, which is Suralaya Unit 6. That's one of our 23 highest emitting plants because it is a plant that runs extremely high rate. It is very important to the Indonesian grid. We've also chosen Python 1 Unit 2. It is the plant with the seawater FGD that I talked about that is very interesting because we want to know whether our estimate is wrong for that plant, or if it is correct, then we want to come up with a strategy that we know could be quite simple for capturing the mercury in that plant. At the same time, being cognizant that we don't want that mercury to end up in the local bay. And finally, Ombel in Unit 1, if we go back to that graph of the cleanest burning plants, the grams of mercury per gigawatt hour, Ombelen was one of those outliers on the far left because it is an older unit. It's about to close if it hasn't closed already. It's running very inefficiently. And because it's about to close and be upgraded, it's an ideal candidate for us to get our feet on the ground right now and make some changes. Now, I'm hoping Wojciech is online as I'm about to hand over control to him. Wojciech, are you there? Are you muted? Hello, Wojciech. Okay, no Wojciech?
Please wake up, Wojciech.
Wojciech, are you there? It's 4 o'clock in the morning in North Carolina. What I'll do is I'll keep talking, and Wojciech, if you're there, you can join in. Otherwise, I'm going to be winging it through your presentation. Wojciech? Okay. Bear in mind, these are no longer my slides, but I will do my best. Okay, so Suralaya is one of our high-ranking plants. It's running at high capacity. It's super important to the Indonesian coal grid, and it has a relatively high.
Hello, Lesley.
Hey,
I'm sorry to interrupt, Wojciech.
Okay, Wojciech, you take over. I'll move the slides. Thank you.
So sorry for that. I've been muted by organizer, but now it came into green, so I'm good. Yeah, thank you. So let me pick up from here. And again, these are plants that we have selected, 3 plants that we have selected for future study. These are not by any means quote unquote worst plants. There are multiple considerations going into selection, including what Les described and costs and feasibility, all this fairly complex issues. So first one is Suralaya. It's high-ranking plant, as you have seen, emitting big amounts of mercury and SO2. It uses relatively high sulfur coal, about 1% sulfur, which is pretty high for Indonesia. Next, please. So let me go to my favorite tool, the iPOG, and these are again, to answer the question from one of attendees previously. This is using actual data for Suralaya Unit 6 to the best of our knowledge based on available data. And again, we would hope to refine this information with technical staff from Suralaya if we decide to proceed with that unit. So, initial screen, as you recall, includes a selection of air pollution control technologies. In this case, we only know of ESP at this unit, and we've assumed 98% particulate matter removal efficiency. There's no known SO2 controls or post-combustion NOx control systems at this unit. Next slide, please. Which will be call information. The information that we have, it's a fairly good call, sub bituminous call with again almost 1% of sulfur, which is high for Indonesia, and a reasonable amount of chlorine, 0.015% of chlorine. Fairly high mercury content, over 100 ppbs. To our knowledge, there is no blending going on at Suralaya 6, so we have used that one single call. Next, please. Some information about boiler. It's a 600 megawatt unit, and we've assumed a load of 100%, and I should stress assumed, as this was the same type of procedure we've used to define economizer. We've assumed it to be fairly tight system with 3.5% oxygen and loss on ignition, as is shown on screen. Again, we would hope to refine these numbers with Suralaya. So this leads us to the next slide, which gives results. So based on the input that I just presented, that we have at this point, iPOG estimated that about almost 30 grams of mercury per hour is going through the stack at Suralaya, while a lot of it is, majority of it is elemental mercury, over 80%, and the rest oxidized mercury. Fairly poor mercury control, mercury removal by the ESP at only above 3%. ESPs, by the way, can achieve up to about 20-25% maybe of mercury removal. However, this is not to say that this ESP is not working properly. It depends on chemistry. It depends on how much unburned carbon there is, how much oxidized mercury. So this is the number, this is a snapshot, this is the number that we have, 3.5%. Next, please. Which is very exciting for us, Unit Python 1, Unit 2, which, as you recall from previous slides, is significant with emissions of relatively high mercury emission numbers, despite having seawater FGD installed. I should mention here that that iPOG is currently not configured to consider seawater FGD. So for the purpose of this exercise, we've assumed that seawater FGD, as far as chemistry in the scrubber, chemistry of mercury, would behave very similarly to limestone FGD. But again, it's only assumption. This needs to be refined. Because of relatively high mercury emissions and having this wet FGD installed, there is potential to increase mercury capture in the system considerably, I would say. But there is big but. The important thing is, and I will focus on it more in the next slide, I believe, that seawater FGD, which is characteristic with ocean water being returned to its origin, to the ocean, has potential to increase local mercury concentration in seawater. So this obviously must be avoided because to protect fishing areas and seafood quality. Next, please. So just briefly, the FGD schematic. On the first glance, it looks very similar to limestone wet FGD. You know, we dramatically increasing specific surface area for mass transfer by finely atomizing liquid. We decreasing liquid phase resistance, but using alkali from seawater. But there are significant differences. Whereas typical wet limestone FGD scrubber would operate somewhere typically between 7.2, maybe 7.4, seawater FGD can be 8 and above. So we don't know at this point how this difference in pH will affect the chemistry here in the tank, how much potential for re-emission of mercury can happen. And I should perhaps introduce the term of re-emission. Well, when mercury goes into wet scrubber, and assuming it's oxidized and mixed of oxidized and elemental mercury, mercury is practically insoluble in insolubles, so it goes right through. However, oxidized mercury is soluble and it therefore has potential to be captured in the wet scrubber. But depending on the chemistry in the hold tank here at the absorber, oxidized mercury that's been captured and transferred into liquid may get reduced to elemental mercury, and therefore elemental mercury will escape. That's what we're calling re-emission. So going back to pH difference, we understand fairly well how to prevent and how to counteract mercury emission for wet limestone scrubber, but we will need to verify that this assumptions, that this practice is good and feasible for seawater FGD. Where the big difference comes is in this step, which is seawater treatment. Because seawater FGD has been, as name implies, has been designed to control sulfur dioxide before the scrubbing liquor can be returned to the ocean. It has to be aerated to improve sulfate to sulfide ratio. We want more sulfate. In the process, we may be creating potential for mercury re-emission from this aeration tank again. And obviously, while wet FGD is quite efficient for SO2, we really, once we put mercury into consideration, we really need to be very careful to understand this stream going out to sea to make sure that there is no or minimal amount of mercury going back to the sea. Next, please. So these are some calculations for Python 1 unit number 2. We have inputted the information. You will see that there is wet scrubber here with ESP, of course, and wet scrubber. And model predicts about slightly above 10% removal of mercury. What is noticeable is that majority, crushing majority, almost all of mercury is elemental, which is no surprise because, as we've discussed, oxidized has probably been captured here. The problem is the fate of what's been captured. So we have about slightly above 10% removal. As Lesley indicated before, we can expect actually up to close to 90% maximum removal of mercury for wet FGD according to BAD documents issued by UN. So between 90 and 10, there is huge room for improvement, which we would hope to achieve. Next, please. And finally, umbilicin unit number 1. It's smaller, and the arrow points to the smaller units. I don't remember which one is umbilicin here, but this is an older mine mouth unit that is smaller than 100 megawatt. It is significant with very high mercury emission intensity, and it is, because of its size, it didn't appear well, didn't have enough granularity. We didn't have enough granularity to show it in ranking. But it's an older unit. It's due for upgrade. So we believe we are, if decision is made to proceed with this unit, we believe we are in a sweet spot for implementation of multi-pollutant strategy for this unit. Next, please. So a few words about umbilicin 1. There are 2 units, unit 1 and 2. Each one is 100 megawatt. They operate at lower operating efficiency than average for Indonesian fleet. So clearly they're a little bit out of line. Firing not too bad, 0.6% sulfur coal, but still it's relatively high for Indonesia. Indonesia is generally blessed with low sulfur coals. And because of age and lower efficiency, this unit is particular with higher mercury emission intensity than what we have observed for larger units. After plant modification, we have considerable lifetime left for this unit. Next, please, which will be the iPOG. So iPOG predicts for this unit only about 12% removal, which is actually not too bad for ESP only. You recall Soralaya was about 3.5. And what is interesting is that speciation of mercury is a little bit different here. It's about half and half between elemental and oxidized. But again, there is considerable room for improvement, given that there is a lot of oxidized mercury going through the stack, and oxidized mercury being quote unquote easier to remove. Next, please. Okay, Lesley, would you like to take over, or do you want me to continue? I don't hear you, so I'll go ahead. So we have identified, we have dropped the shroud. We have identified three plans for next phase. One for each group that we have discussed, and we have modeled these plans with iPOG. Plans were selected using all this criteria that we have mentioned, but also importantly with the goal to make it easier to duplicate this approach across the fleet in Indonesia. I mean, it is good and nice if we could improve 3 plants, but it would be nicer if we could improve almost all of them by copying this approach to other units. You have heard me saying estimate, assumption, estimate, assumption. These are not the good words when we about to make serious decisions. So we need more information from stakeholders. We need them to confirm that yes, the coal we are considering, we are using it, we're not blending, we haven't switched to lower mercury coal, we are having installed anything. Most interestingly, if there is any information of measurement of mercury emissions at these plants, that would be most useful. So in the next phase, site visits were also proposed for interested parties in conjunction with MEC 15, which will be held, is planned to be held this fall in Bali, COVID permitting and God permitting. So this is all we have, I believe. Thank you, and we will try to answer questions.
Thank you, Wojciech. Thanks for that. Yes, that is what we have so far. I wonder if our panelists want to pop their webcams on, those that want to be involved in this discussion. There are a few questions that have come in, so I'm going to run through those, and whoever's up for answering them can do so. We've covered how many power plants. It says here, one for you, Wojciech, if we can put all the parameters into the iPOG, what do we do if we don't have any information on chlorine content?
Well, we can measure it in cooperation with the plant. Once plants typically have long-term contracts for coal delivery, so we could take sample and measure, analyze coal and measure chlorine.
There is also the option in the iPOG to choose a standard subbituminous coal, which will have a standard chlorine content. Is that right?
Yeah, we can do either. We can choose standard or we can modify.
Excellent, thank you. Do we study the cost of implementing controls? We're going to deal with that tomorrow. We'll hand over to Roger for that tomorrow morning. Somebody wants to, sorry, missed the meaning of the term lifetime. Good question. Yes, the lifetime, we assumed that plants will run until they're 40 years old, which is a huge assumption. Some plants will close earlier. This was just for this particular business as usual worst case scenario estimate. As we say, we've handed over this database to the Indonesian stakeholders. So if they want to start closing plants at say 25 years old, they just need to change that little bit in the spreadsheet, Paul, can't they? And they can change the estimate entirely. It's an extremely useful data set to play with. All we did at this point was this worst case scenario so that we could demonstrate that if we can identify these high emitting plants with long lifetimes that are being used a lot, then they're emitting 40 to 50% out of 10 to 15 units out of 100. And that is a huge piece of information for stakeholders to know that by targeting just a few of these plants and spending money on a few of these plants, they can reduce emissions significantly without, I don't want to say wasting money, but without spreading the cost across all the coal plants, many of which will not give return on investments for some of these control technologies. Okay, I think this is a question for you, Wojciech. What is the analytical method for mercury in coal?
Well, there's number of methods, and one of them is digestion when analysis by atomic absorption.
Yep. For the analysis in coal, Techmira in Indonesia did some of the analysis, as did the US Geological Survey, I believe, for the initial study. Anton's nodding. Yes. Another question.
That's very good progress. Thank you for bringing it up. This is again discussed in detail in the 2017 report.
Thank you. There's a question I'm going to throw at Paul, since your face is there. How long is the average lifetime of a coal plant?
In Indonesia? Well, if it's in Indonesia, I'll pass that to Anton, but average lifetime can be anything between 50 to 60 years. Even the United States, I've seen lifetimes go way beyond that. And we're also seeing recycling rates in China where they're replacing their plants at 25 years. So very, very open question, but theoretically, looking at anything up to 60 years.
Thank you. But of course, there are new policies in places such as China to cap coal age to 25 years, is that right? With the idea being that you phase out the older units and you put in the supercritical and ultra supercritical.
I believe that's the case, yeah. And so that's how they've managed to get their fleet efficiency up, but at a very, very, in a very, very short space of time, yeah.
Yeah, the Chinese have done amazing stuff. Questions come in from Yong Chun. Are these 3 units fitted with ESP, Wojciech? Can you remember if all the 3 units we studied? And
Yes, Baruya has it, Python has it, of course, for wet FGD, and Umbilin has it as well.
I believe ESPs are on most of the units in Indonesia. Is that right, Paul and Anton?
I believe so.
Okay. Why is the speciation of the Mercury different between these facilities, Wojciech?
Oh, I wish I knew exactly, but some of compelling factors, maybe amount of chlorine in coal, maybe effectiveness of combustion in terms of how much unburned carbon or LOI is there in the flue gas. Then, of course, having wet FGD like at Python dramatically switches speciation towards elemental mercury, because a lot of oxidized mercury, at least initially, has been captured. So there are multiple factors to that.
Thank you. Roger, are you lurking in the background? I'm going to throw a question at you if you're there.
I'm here, yes, yeah.
Perfect. I have a question. Is the mercury in FGD wastewater, does that need to be treated?
That depends on your wastewater limit, but ultimately, if you want to stop that mercury from leaving the plant as best you can, then yes, some water treatment will be required, and I do touch on that subject a little bit tomorrow.
Excellent. But in the majority of, because I think I muddled it up earlier, in a normal wet limestone FGD system, most of the mercury is going to end up in the solid waste. Is that correct?
That's certainly what you'd like to achieve. But the key thing about the limestone FGD in comparison to a seawater FGD is the wastewater flow is tiny relative to a seawater process FGD. So your ability to treat that, in principle at least, is a lot better.
Okay, well, as far as I can see, that is all our questions that are in so far. Anton, do you want to make a comment before we close up for the day and move on? No? Is Anton muted?
Yes, okay, thank you. So, sorry, I have difficulties to unmute myself. Anyway, I guess today's is quite well. There is a lot of question also from audience, and from my side, I don't have any other further comment or requests. And thank you so much for a wonderful presentation from Lesley, Wojciech, and then of course tomorrow will be continued again, Roger and other teams. So thank you so much.
Thank you. We have a few more questions that have come in at the last minute, but I think we will leave them tomorrow because I can see that some of them actually relate to control technology. So hopefully Roger will deal with that in the morning. Now that you know how to use the question function, audience, please do send us your questions and we will deal with them as best we can. We don't mind finishing up early. If everybody's happy with what's been presented so far, then we are happy. And we look forward to seeing you tomorrow morning. Oh, hang on, Anton wants to say something.
Sorry, please take note of the remaining question, Lesley. Do not forget so to answer it all by tomorrow, so audience can be happy and then come back again for tomorrow.
Okay, well, in that case, hang on. Let me just look. Think. Why do the power plants with the high sulfur concentrations in coal not have desulfurization? I can answer that. Indonesia has only just implemented sulfur control legislation. So it is new plants, all new plants are being installed with desulfurization control technologies. And a lot of the plants are actually firing compliance coals, low sulfur coals as well. But desulfurization will happen retrospectively. So many of these older units, which will continue to run, will have desulfurization applied in future, I believe.
Can I also add to that?
Sorry?
If I can add to that, that's
Please do.
Yeah, a lot of plants across Southeast Asia that are importing Indonesian coal also have the term CF in the World Electric Power Plant Space, which is compliance fuel. So they don't have a requirement for FGD, but when you're burning a 0.1% sulfur coal compared to anything up to 1%, which you might get exported from the USA, it's extremely low sulfur, almost negligible amounts. That's why FGD is not required. If I could return to the ESP question, apologies. Most of the large plants have ESP, but quite a few don't, because actually, Wojciech, you presented a coal there, which was 3.8% ash, which is very, very low. That's getting on to a very low ash that you'd expect in coking coal. So that's a really clean steam coal, and so therefore ESP may not be required under those circumstances. Thanks.
Thank you, Paul. Appreciate that. Okay, I think this might be one for Wojciech. Based on the modelling by the iPOG, mercury removal efficiency is not very high. How much efficiency would be achieved, should be achieved to align with the roadmap for Indonesia? That's a huge question.
Yeah, it is, and that's why we need phase 2 to define based on current legislation in Indonesia, what are the requirements for power plants, how much mercury do they need to remove to make their units compliant with the law. In general terms, and referring to BAT, mercury, depending on air pollution control configuration, if power plant has only ESP and everything goes well in terms of speciation, combustion, chlorine, and all these factors, we can expect up to about 20% removal. If again, these are just examples, not exact numbers. If we have combination of ESP and wet FGD, we can expect high 80s, maybe touching 90% removal of mercury between ESP and FGD. If we have, which I don't believe are existing units in Indonesia, with SCR, selective catalytic reduction for control of oxides of nitrogen, then we can, and FGD on top of it, we can then expect well in the excess of 90% removal of mercury. But again, we need to refine, we need to understand exactly what we need, what is at each of 3 selected plants, and how much requirements these plants have, and then we will need to tailor control technology.
Perfect answer. Thank you very much. More questions are coming in. We're obviously piqued people's interest. This is perfect. So let's keep going. One for you, Paul. Does the coal sample of a power plant change frequently? I guess that does the coal that a power plant uses, does that change frequently, or do they stick with the same coal?
I'll be honest with that. I don't know. Not in the case of Indonesian coal plants, but typically, yeah, they will definitely stick with the same blend, not necessarily the same coal. Frequently they will test a particular unit, a different coal, but those would be a negligible amount compared to the overall tonnage of the inputs. So the answer to that is they'll stick with the same blend.
Roger's nodding. He might. Oh no, Anton, please.
Thank you, Lesley. So usually there is a long-term contract of the power plant with the coal supplier. However, for a huge power plant, for example, like Suralaya, they have a lot of suppliers also. So this is make management also, difficult to handle, because of course, if you have a nine different supplier, you will have 9 different characteristics of the coal, and in order to supply the unit on the unit, you will have to adjust what you call it in order to fulfill the requirement of the unit itself. So whether you have to blend supplier 1 and supplier 2, or supplier 2 and supplier 3, or blend a lot of what you call it coal, and the impact on the blending, you will have a a huge variety of coal characteristics, something like that. And the one that we did in 2017 is we took sample from the feed of the unit. So it means although the supplier is the same, the changing on the blending can also impact on this activity and the emission that will be released by the unit itself. Thank you.
Thank you, Anton, for that clarification. Okay, next questions come in. I guess this is for me. Does the IEA Clean Coal Centre plan to run pilot work such as installing Mercury solution in the substream? I'm guessing this is asking you what kind of project work we can do. We're actually going to touch on this more tomorrow. We have no funding for a demonstration project as such. However, we have funding to find funding, if that makes sense. And we're hoping to work with the US Trade Development Association and anyone else we can get our hands on to perhaps set up some more investigative work at these 3 plants to get some information to make sure that the data we put into the iPOG is correct, and to get more plant-specific information so that anyone who wishes to submit a proposal has as much information as they need to do so. However, we haven't got to that stage yet, so we'll leave that question and hopefully I'll be able to answer that in a couple of months for you. Next question, I think this is for you, Wojciech. I would like to confirm on whether the iPOG could only take one specific set of coal parameters or not. If this is given case, and sorry, tiny box, a constant coal parameter throughout the operating years is assumed. That is true. How do you deal with coal quality fluctuations? Thank you.
Well, it's a multi-layer question. The first part of the answer is that yes, iPOG can either analyze for 1 coal or can analyze for blends up to 3 coals, and then it can use one of coals from its own library, whether it's lignite, some bituminous, high sulfur, low sulfur. But once it assumes the coal, there is no way for iPOG at this point to account for variability. We just need to assume, and this I think goes back to what Anton explained a moment ago, that power plants typically have long-term contracts, and it's not only for the reasons of air pollution control equipment, but there is for new type of coal, plant needs to be fine-tuned. Ball mills need to be rearranged. Temperatures may be different. It's quite costly and quite complicated for plants to switch from coal. So they wouldn't do it from month to month. they love to operate for an extended period of time. But answer to the second part of the question is no, iPOG cannot account for variability, whether it's from day to day or which is impossible, but month to month, it doesn't account for that.
Thank you, Wojciech. I think this question is for Anton. Are there any monitoring stations around the plants?
Sorry, can you repeat again, Lesley?
Are there any monitoring points around the plant? I guess they're asking, is there ambient monitoring in Indonesia?
At the moment, of course, government has a lot of project and activities also, but in terms of the the power plant itself, of course, they have a CMS that is usually installed in, and it's already recommended by the government, installed in their unit and parameters. And although, of course, although we don't know that the CMS are running functional properly or not, but at least all of the power plant is already encouraged to install the CHAMS. So I guess it is answering the monitoring of emission that is emitted by the power plant itself. But again, the Ministry of Environment also have a monitoring, air quality monitoring also, but not specific in the power plant. I mean, they have in other locations, something like that, just to monitor the quality of environment, especially air in the country, something like that.
Thank you. Okay, I have a question here that could be answered by either Wojciech or Roger, so raise your hand if you want to take it, boys. If the mercury is absorbed in the fly ash, isn't it perceived as a hazardous waste? Nobody wants to play? Okay, I'll take it. I actually wrote a blog on this the other day. The EPA has done years of study on this, and they wrote a review study in 2014 in which they said that mercury in fly ash is fairly well stuck in that fly ash. It's stuck to the unburnt carbon and other solid materials coming out of the plant. And they've tested leaching on it, and they have defined it as not a hazardous waste. They don't believe it leaches in any situation. And in fact, they say that the mercury leaching from fly ash is actually less than from other materials that can be used in cement and concrete. As far as they're concerned, fly ash is actually safer in concrete than some other aggregate materials. So the question is, I presume there was an article in Monga Bay, the journal last week, that said that Indonesia is sending most of its fly ash to hazardous waste, and it should continue to do so and shouldn't use it in cement and concrete, where in my opinion that is entirely wrong. Fly ash is super useful in cement and concrete. In fact, the Netherlands import fly ash from other countries, as many countries do. It is cheap. It is madness to stick something into a waste pile, to lose that land, to store it as hazardous and make it scary for years to come, whereas in actual fact, if you stick it in cement and concrete, it's safe as houses, literally, and is a free resource. Jakarta is sinking. There's a lot of material that needs to be produced for building in Indonesia, and the fly ash is there. It's free, it's easy to use, and it's safe, in my opinion. So that's my opinion. I do have an opinion on that. Thank you, Anton. Yes?
Thank you. I'm also happy with this new development of fly ash bottom ash in Indonesia. It is much safer to use it as a concrete material rather than, for example, I'm sorry, but this is really happened when I was able to visit Ombilin. I saw a big, huge of stockpile of fly ash bottom ash, and then just sitting there. So it is much safer to put it in concrete rather than just it in the landfill or somewhere else, because when you put it there, there is a big possibility that the heavy metal will leach during the rain comes. So it will much worse rather than we use it and then put it in the concrete. So I guess this is a good, very huge development of the fly ash and bottom ash in Indonesia. Thank you so much.
Thank you.
And there's a significant carbon benefit as well in using fly ash in that application as well. So, you know, if we just move away from Mercury for a moment, because you're using the fly ash instead of other materials, which in their production involve CO2. So you're saving carbon in that sense. So it's all around a good thing to use fly ash if you can.
Excellent, thank you for that. Another question for Wojciech, I think. What is the actual effect of chlorine in coal on mercury emissions? I want to understand the exact contribution for the differentiation in mercury emissions. So clarify the effect of chlorine, please, Wojciech.
Chlorine is beneficial for mercury removal. In fact, addition of chlorine to coal is one of methods that can improve mercury removal across the system with wet FGD. What chlorine does, step back. Initially, when coal is injected into the furnace, everything is vaporized, including chlorine and mercury. And then as flue gas cools down, going through passages of ducts and equipment on its way to the stack, equilibrium develops that chlorine reacts with gaseous mercury, and then oxidized mercury is then either attaching itself to unburned carbon of fine particles of fly ash, or is solubilized and thus removed in wet FGD. Similar effect can be achieved by bromine addition, which is another method of controlling mercury emissions from coal. So it is advantageous to have high chlorine content in coal. Of course, everything has its price. If chlorine concentration is too high, there is increased potential for corrosion of equipment. However, this can be mitigated by actual injection of small amounts of alkaline dust, for example, out front of ESP. So chlorine is very good for mercury.
Thank you. Nicely clarified. Okay, I think this question is for Anton. Are you ready, Anton? Is it only coal that's burned in power plants in Indonesia, or like in Germany, they co-fire sewage sludge? Is there any co-firing of sludge or other materials in coal plants, or just coal?
At the moment, as far as I know, it's only coal. There is no sophisticated other technology that is, for example, like they burn coal with I don't know, biomass or whatever. But at the moment, it's coal, because coal in Indonesia is relatively cheap. But the problem is I haven't seen a power plant that use coal wash yet. I mean, coal that is already being treated. So usually they just use coal as it is. But of course, there is a different quality of coal. But if it's just coal right away, that is mining from the mining side, something like that.
Thank you. Yes, co-firing adds a whole lot of new issues. The Clean Coal Centre has a lot of reports on co-firing. You can reduce emissions by co-firing with sewage sludge and biomass materials. However, you do have to work out where those materials come from and how they may affect your emissions. We do know from some of the studies that if you co-fire sewage sludge, you can significantly increase emissions of mercury and other trace elements, as the human body is quite good at concentrating them into waste materials. Okay, another question, which is perhaps for myself and Wojciech. Do we have any data on mercury emissions from South Africa, and how test work can be advanced in this field for local industries. Wojciech, do you want to take that one? Anything from
Sure,
South Africa?
sure, thanks. Yeah, I would refer this person asking question again to the website of Coal Combustion Partnership for UN. There is a mirror report, what we have been referring to as 2017 study for Indonesia. There is a mirror report for South Africa. In fact, there is another one for China and Russia. This was done before the study in Indonesia, so probably 2015-16, this time frame. But similar work frame for similar to Indonesian report in that coal supply and production was defined in for each country. Then coal combustion fleet was defined in terms of air pollution efficiency and all this. So yes, there is information for South Africa, and in fact, with contributions from U.S. Environmental Protection Agency, we were able to measure mercury emissions using method 30B, carbon traps, at I believe 3 or even 5 power plants in South Africa. So there is information.
Thank you. I think this question might be for Anton. Does the Indonesian government or power plant owner plan to construct and operate the recycle plant of mercury, such as burning and recorrecting? I don't know what that means, because you don't recycle mercury in a plant. I guess the question is the Indonesian government planning to put any mercury control technologies on their plants?
Of course, perhaps I'm not the right person to answer that, but I will try to answer on behalf of the ministry. At the moment, a new policy has been issued on the mercury standard on the emission, especially in the stationary source, which is specific on coal-fired power plant. And with this kind of a government regulation, of course, the power plant should also aware, and then also should limit their emission to the environment, something like that. And regarding with the recycling of mercury, I don't know whether I catch this correct, but in Indonesia, we don't have a facility to how you call it, to recycle mercury yet. I mean, usually the company that are recycling of mercury usually are the thing that I heard is in developed country like Japan and others, something like that. But mercury that is something like managed in Indonesia, usually is sent out of the country because we don't have also a final storage in Indonesia. But we have now also a national action plan on mercury reduction, and it is already in terms of government regulation also. So all of ministries related stakeholders are working hand in hand on dealing with this issue also in the country. Thank you so much.
Thank you. Well, and perhaps a follow-up question to that. Somebody's saying, okay, they understand that there is now action being taken at the coal-fired power plants. Does Indonesia have any mercury legislation imminent for waste combustion, smelting and cement for the other sectors?
I'm not sure, I have to check the regulation, but for stationary sources, yes, there is already regulation And I'm sorry, but I guess yes, for waste incinerator, specific on that also, because for the coal-fired power plant, usually the mercury are the concentration of mercury in the coal are relatively stable, but we can think that in the waste incineration of sometimes you don't produce mercury emission at all, but sometimes if you put a waste with mercury inside, so you will at the time you will produce huge concentration of mercury being emitted. So yes, the government have or put regulation on stationary source, and particularly on the coal-fired power plant and also waste incineration and the cement at the moment.
Thank you. I have a comment that's come in. Somebody's asking about biomass, and then somebody else has answered that by saying a few of the power plants in Indonesia are starting to co-fire with biomass in the future. It's certainly been discussed by some of the utilities, which is great. Somebody has asked for the emission limit, has question mark, is it 0.03 milligrams per meter cubed? It is, it's 30 micrograms per cubic meter, the mercury emission limit that has been introduced for new plants in Indonesia right now. This is a similar emission limit to what has been applied in North America, Europe and China in the past. I think it still applies to most plants in China. These countries are tightening their emission limits, but they can do that because they have flue gas desulfurization and DeNOx technologies in place for most of these units, and so they can meet emission limits that are an order of magnitude tighter than that. And Indonesia in future, now that it has an emission limit, can certainly move towards tightening that within the next decade or so, and they would achieve that if they continue to install FGD technologies and so on, we would hope. That is our last question for today. Thanks, everybody. That worked really well. Thank you very much, panelists. That was great. And now that the audience know that they can put these questions in, we hope to see lots of questions for Roger, who's on first thing tomorrow morning. And then we have more time for discussion tomorrow. So if you are returning tomorrow, please do come with questions. We have plenty of time. I think we have a full hour dedicated to answer your questions, and we would love to do that. If you don't ask us questions, then Wojciech will take you through a demonstration of the iPOG, which is always good fun to show you how to use it. You can download it yourself and you can play with it yourself, and you can see what a useful tool it is. But it would be great if we could genuinely answer the questions that you have. In front of you is a panel of experts. We know what they're doing. We have access to the Indonesian stakeholders. There must be questions you're desperate to ask. So please do tune in tomorrow and ask those questions. So I'll close up today by saying thank you very much to all our speakers, to our panelists, to the people that asked the questions, and to everyone for paying attention. And I look forward to seeing you tomorrow morning. Thank you.
Thank you. Bye-bye.
Bye-bye.